Good day, everyone. This is Jamal here again. And in this video, I'll be working on one idea I have on finishing my paper on the magic square of squares problem. And so far, what is left for me is that I was building an approach to work on this problem, and I've been able to get some ideas on how best to approach finding a magic square of squares of seven integers, even though that's already known case. But since my paper is an incremental one, building on one case after the other, the goal would have been to find one example for each case I work on. Probably aside from the case of where we have all nine integers, where there's no known such example, and quite a lot of speculation that it doesn't exist, and all of these things. But I've had some. I've been able to build some ideas around seven integers and two non-integers. So my goal was to test that idea on an already known example. Because if once my idea is correct and it's fundamentally right, it should work for the example we already know of. So here I'm going to test out that case, and I'd already begun, but I mean the core of what's left to be done is what to handle in this video. So I'll share my screen over here. So here, uh, let me download once again, and let me see here. So we'll now do this. We'll drag this here. Layout. We'll show only the PDF so that everything is visible. So this is the point I had gotten to. Yeah. So initially, since we already had a case where we had five integers and four non-integers, the idea was to solve two other equations simultaneously. So I decided to go after g squared and c squared, you know. So let's go to page 13 to see what I'm talking about. I labeled that as theorem 2.4. So page 13. Yeah. So this was the theorem I had regarding this. So these were the integer side and then non-integer sides. So in order to get seven integers out of nine integers in a magic square of squares, the goal would have been would have either been to solve these two as a system, or these two as a system, or these two as a system. But from the look of things, it's more feasible to solve these two together. Since they are conjugates, it's much easier to solve them as a system. So mm, this was how we chose to handle things. Yeah. So right now, I decided to work on g squared and c squared being simultaneously, like solve them as a system. So we look at these two equations, and because we realize that given the approach we took, given that g is bigger than c, as established in this paper, and in fact, it isn't that g is strictly just larger than c, but it has to also do with symmetry. Because when you come over here, let's go to the first page. Um, when you look here, Um, for instance, when you look at when you look at this, for instance, if you had to switch sides a bit, you could get c squared minus g squared equals h squared minus f squared, which is still about the same thing. Here you could equally say c squared minus g squared equal to d squared minus b squared. It's just about the same thing, just about a matter of symmetry. So coming back over here, but because of the approach we took, we have to now say g squared is bigger than c in this case. So in this case, you have to recognize that c is now um, g minus t, you know, and so we did this expansion over here, and then we got this, we worked things out. So we decided to just test our idea on an already known example, and this is the already known example by Andrew Bremner. So you're able to determine now for the case equal to one, to be able to test our equations, our formulas for the unknowns on this particular example. We decided to test this equal to our formula for this, and we're able to easily determine that since this was prime, um, it's a matter of now solving this equation to see what happens. So let's go to Wolfram alpha. We bring this close here, and when we did that, we found out that x, okay, here equals 18, y is equal to 7, and because r subscript 2 is bigger than r subscript 3, we now take it that r subscript 2 is now 18 and r subscript 3 is 7. So with that idea in mind, you're going to have to cite this. So let's do this. Copy, paste. And then we go here. The only thing where we are going to deep seek right now is to get it to how do I cite this in overleaf? Let's see. So we now come here. Yeah, today is 12th October. October. Ish. Nah, no, what? Let me do this. Okay. Yeah. See. Now let's see. Good. Mm. Would have to be solved for integers. And thinking of something. Let's spell that k is equal. We now realize that r subscript 2 equals 18 and r subscript 3 equals 7. Yeah. So right now, since you have not been able to determine what are the values of um um k, r2 and r3, the only goal would now be to substitute all of this into the formulas as we've had it. So with reference to theorem 2.4, yeah. So right now, to save us also time, to save us time, what we will do is this. We'll go to equation theorem 2.4. Where is that guy? Which is also on page 13. 6 integers center. So we will now take all of these formulas. We'll now go to this one. Let's see. Okay. Now let's make a new chat. Given that we just get, uh, I mean, we are not depending on this to do the work for us. We're just getting to compute things for us just to save time, So that's why I'm just using this. 18 R3 is equal to 7. K equals 1. Mhm. Let's do this. Whatever values you get, to compare to the already known examples and we'll see what happens. Okay, the values are looking alike. Yeah, let's see. Think must have see. Think it's like must have. Yeah, my phone is over there. I'll get my phone. Yeah. Yes, it's here. Just to test something. Coming. Let's see. Is it done? Huh. We can't trust this, obviously. We can't trust this. I don't know. Aside the formula that looks right for the first one, I think we'll just do it on our own. So we take this, all of this, and so we'll come here. And I think, let me see. Let's test ChatGPT and see something. Let's see how well it would fare. Whether it's gonna be great or play games. And so, what do I do? This thing, yeah. I'm just going to experiment with something. I want to see how well it would have fared because I don't trust the DeepSeek's result aside from the first one, which I already know is right. So let's see what this guy will tell me. Yeah, let's see how well this would have fared. It's about the same thing. Strange. Okay. Hmm. This I remember. I'm familiar with this. I've seen this before. I've seen this before. I've seen this before. But I think you can use a sort of an absolute sign so that it's positive because when it's positive, it still works. Now let's look at our own formulas and see what happens. What what is our own magic square of squares saying? Okay. Now we'll do things on our own, you know. So now we will okay. We'll now do this. We want to see how already established examples compare to my approach. Mhm. So given we already know this to be 373. Okay, let me ask something. How do there is a LaTeX way of using the absolute sign? Let's see. Okay, okay, divert. Okay. So let's try this and see. I'm using the absolute sign just because it has to be, positive numbers. It works anyways. Uh, I think I should just remove it. Oh, the thing is, I'll send this mail to a professor who works around this problem, get his opinion. If it tells me that they need to put it over there, put it over there. I just want to show that it's just as it's supposed to be. So now A is 373. Let's try this. I'm going to use my calculator now. I think it's much better. So 2, 1, R3 is 7 plus 18 squared minus 7 squared plus R2. R2 is 18. Oh, so in the calculation, the AI generated was correct. Okay, okay. Okay. Let me try this and see. Minus. Okay, let me put this over here. This strange. What is I find it interesting. Wow. 18. I'm now here. So here we get negative 23. But I realized that even if I put negative 23 inside, or even if I put in positive 23 inside the magic square, it will still work because any negative number squared becomes a positive number. And so let's see. Let's see what I looks like. 4. I'm here now. Let's try 18 squared minus 7 squared. What is R3? R3 is 7 plus 18 squared. Oh, wait. Ah, okay. Oh, oh. Let's see what happens when I square it. I'm just beginning to realize that all the numbers are different. The number suggested by the AI was correct, like crazy. Because look at the numbers we are getting. Let me compile it and see what Let me show you what I'm getting. I'll compile. So you can now see over here that I'm getting this. So for this, what it looks even looks somewhat similar. But then when you come and look at this graph here, I'm seeing very wonderful things. A, B, C, D, E, F. Oh, okay. Interesting is that what is interesting is that look at A is here, B, C, D, E, F. Look. And now what appears to be H is now F over here. And what should have been E? What should have been F? What should have been F is now H. Hmm. There's some change. Wow. It's interesting. Interesting. I was even imagining that probably all the integer sides should have been the same as we had it, and the rest would just be whatever they want to be. And maybe we could just blame that on symmetry and try to balance things and see how things would have looked. But I mean, okay, let's see. B is bigger. Okay. Hmm. But still, even if it's no matter what the positions are, the numbers should all be the same somehow. And as far as I've checked, you have not made any errors too. Wow. Normally, hmm. Let's see. We'll keep on testing it and see. I giving us something. Maybe I squared is saying something. It's wild. Okay. We now have a value for one I squared 14822 which is wild. Hmm. I'm thinking of something. Hmm. Wow. Thinking of something right now. Mm. Wow. So now we have another one. This formula for I resembles nothing like this. Not at all in a million years. This is strange. Hmm. That's crazy. King. Because as I'm substituting these values, I realize that, oh, we don't get along. You know what? I'll still go on anyways. Even though here we might be getting five integers out of nine, but then I want to see how correct it is. I want to see if the magic square, if the resulting magic square itself is correct, no problem. Well, I should even introduce this idea of okay, let's keep working. Regardless, we keep working. Um, we are now. I'm not doing the one for C. I'm now going to work on this formula for C. I'm now here now. Hmm. R2 is 18 squared over 2. Okay, let's see what ChatGPT give an answer like that. Let's see whether it will see happening. What formula did it give for C? Okay, it's even wrong. Who even takes this guy serious anyways? Okay, let's see something. 7342. Okay, this one is correct. This is correct. But nonetheless, it's good we did it on our own. At least we all see that I don't fully trust these things. So you just have to just use for convenience a bit, just instead of, maybe ask how do I use this reference, or sometimes it also saves me time typing, but mm, it's very important that we do our own work anyways. So C is equal to 14684 753 over 2, which is just, another way of expressing those formulas that you saw. So we come back here, and we don't do too much work here for Jane than to, let's see what DeepSeek said. 7619, yeah, it's correct. Mm-hmm. Now the formula for E becomes very simple. The only job now is the formula to remove those other guys. And now E is only something like, they definitely know how we anticipated things, but it's just the numbers. So 7443164. We have all nine now. Let me see, A, B, C. Hmm. Wow. So just later we have 5 out of 9. This string. Okay. Let me pose this to ChatGPT and try something. Once again, we're just testing something. Because if it happens that all the magic squares is all correct, all the sums are correct, and it means that my approach is still correct, but you just have to approach things a bit differently. My approach will lead to special types of solutions. Um, let's see what it says. Hmm. So the movies that make us, okay. Let's see. Let's see. Garbage like we expect. Now let's experiment. We're just experimenting something. We'll just work it out on ourselves. Uh, let's try something. Hmm, this crazy one. Let's see. Let's see what it says. That even brings something to my mind. Okay. E, G, I, mm. I think we'll have to test our own thing in our own. We'll have to test it because we can't trust these ones. We can't really trust them. Indeed. So, well, if the constant sums are correct, it would mean that, no, it doesn't mean that our approach so far has been wrong. But like I said before, it means that we're gonna get a special type of integers that work for my approach. Which is interesting. Let's see. So I'm going with A, B, C to test something. What is C? 468 47532. Hmm. So I've gotten ABC. I'm now going to do AD plus A squared plus D squared plus G squared. AD 3832. 239. I still get the same thing. So I'm still not done, but let us look at a magic square of this sort. So we are, so right now we have done, let me lay out. So far, I just tested this and it worked. And I just tested this and this works. So now we are now going to test G, test this and C. One, 822, 824. Correct. Correct. So far, as much as I've tested this, and that, we've gotten the same numbers. Now let's test this now. No. Even though you're not dealing with all the eight or all nine magic square integers like we want. In fact, in this case, we even expect to get 7 out of 9, like the odd known example. But whatever we are getting, you just have to make sure at least the sums adds up at least. So let's focus on CFI now. C plus F is 527. And what is I? 14822 824. Yes. So far, I've tested all four sides. They are all correct. So, okay, okay. So far, what do we do? We are now going to test. If I've tested here, it works, here works, here works, here works. Now let us test this and see what happens. AEI. Hmm? Plus AEI 14822 824. And so far, okay. Let me see. Did I calculate something wrong for E? Mm. Uh-huh. Okay, I see it now. I see it now. I missed something. I did not include, okay, 7 squared, good. Good, thank God. So I'll easily correct this. This is good. So it's good to catch these things in time. Mhm. So we have made those corrections. Now let's do this and see. Um, yeah. So we're supposed to test a squared plus e squared plus I squared. Now we've gotten what we wanted now. So 1496 1953. Yes. We got it now. We got it right now. So far, we've now got five correct. Now let's do c squared plus e squared plus g squared. Let's see. 4753 c squared plus 15239 I didn't realize it's not all yet. 4961953. Correct. Haha. And um, so far we now have six corrects. So far, we just tested this. Now we are now going to test this now. Each 23 squared. Now we now have seven good sums out of eight. We are now going to test the last one. So we're not going to test this. Once it's correct, that then means that even though this did not go like we wanted, but it does not mean our approaches are wrong. This is a particularly I think this one is an approach on its own. So let's do it. D a 3832 squared plus E 1496 over here. 1953 to B D E F plus 527 squared. Yes. So all eight sums are correct. Oh, it's just that I recognize some of the terms. So for what you can do is to recognize the fact that to can come and see, having tested this approach to already known examples to the already example of Bremner, it is observable that three out of the five integers generated in the values above for instance, I took off 373, 527, and 23. Let's see. Okay, let's do this. Yeah. Hmm. Okay. So right now, yeah, this is what we are working on right now. My on my blog. This is what you're actually doing right now. So we can edit it. Edit my blog. Edit. So all this comes here. We remove this and come here and then receive. Hmm. But this actually from these formulas we develop are interesting in its own way. You know, it's interesting because how is it that it doesn't give us the expected results, but it still doesn't feel in its correctness? You know, right now I think I'll just move this. I don't have any idea of anything else to add. So I'm done. I think I'm done. I'm just thinking. What, based on the expert feedbacks I received exactly a week now, I've gone on to make certain improvements in my paper, and I think I've been able to improve this paper to a certain point. So I'll still seek expert feedback for this result I had to see how else, what could be done now because I think I've been able to approach this problem to the best of my limited ability. The only thing which would have held me back is computational constraints, which I think that if anyone sees merit in what I've been able in how I've been able to approach this problem, they could use computational means to further expand my approaches. I even have an idea on how to approach 8 integers out of nine, you know, and it's over here. It's like you'd solve this equation as a system, and G over here is just the same as G as you know. If you can solve this as a system as the formula for E squared, I think we can get something. For the formula we generated for I squared, I don't think we can get an integer for that. I'm very skeptical. But I just don't have any formal way of proving that, you know. Because what I've come to realize about that formula is even if you could find a way to manipulate things to get a integer solution for that, it sabotages the rest of the other formulas. that we have, which would work perfectly. So I think it just can't be an integer, you know. Mhm. So so right now I'm thinking of some things to do. Just, uh, I think this is where I stop the video for now. I think this is how best I could have approached this. Mm. Okay, let me do one last thing. Let me go over here. Okay, I'll do this. Just tell him to do this. Label this T1 and G. Let's see. Uh, oh, okay. It's it's built into the outside of the margin, so I'll remove it like that. It's okay. It's no problem. Let me just indicate here once again where okay, let's see where G equals square root. Good. So we are done. We are done. So I think, like I said, this was where we end the video. Thanks very much for watching and ciao. See you next time.